Hello, this is the final part of the 2010 PAT. So this is the long physics question. We got a gun that's designed that it can launch a projectile of mass 10 kilograms at a speed of 200 meters per second. The gun is placed close to a straight horizontal railway line and a line such that the projectile will land further down the line. Right, so it's just firing it along. Small rail car mass 200 kilograms traveling at a speed of 100 meters per second passes the gun just as it's fired. Assuming the gun and the car are at the same level, what angle upwards must the projectile be fired in order that it lands in the rail car? Right, so we need the same horizontal velocity. So that means that we need to get the horizontal component of the projectile, which is going to be 200 cos theta, because it has said, yeah, angle upwards. So angle upwards to me means that. So 200 cos theta has got to be equal to 100. So theta must be equal to 60 degrees. Right, that's a nice starter. How long does it take for the projectile to reach its maximum altitude? Right, so we need our vertical velocity, which is going to be, it was 200, wasn't it? So 200 sine 60 degrees, which equals, well, sine 60 is root 3 over 2. So that's going to be 100 root 3. And that is decreasing at 10 meters per second squared. Decreasing at 10 meters per second squared, i.e. every second we're knocking 10 off of this. So we need to divide that. So time is 100 root 3 divided by 10, which is 10 root 3, which is 17.32 seconds, using the value for root 3 that they've given there. Right, how far is the rail car from the gun when the projectile lands on it? So it's moving at, that was moving at 100 meters per second, wasn't it? So we've got 100 meters per second. We have to multiply by the time of flight. So it's taken 17.32 to go up. It will take 17.32 to go down. So 2 times 17.32. So that is 2, well, we're just doubling 1,732. So 3,464 meters. Cool. Where are we now? Without considering energy, calculate the projectile's maximum altitude. I'm not sure why I would be bothered to deal with energy anyway, because we just need to do average velocity multiplied by time. Is going to be our maximum altitude. So that is 200 sine 60 degrees. That was our starting velocity. It ends on 0, so we just need to halve that. And then we need to multiply it by the time. Don't really fancy putting in the 17, what was it, 17.32, but it was, so that's 200 sine 60 over 10. So 200 sine 60 over 10, that's got to be much easier to deal with in terms of our calculations. So we can get rid of that and that. We're going to have a root 3 over 2 squared, so it's going to be 3/4. We can halve that, so it's going to be 3/4 of 2,000, which is 1,500 meters. Right, so I mean that's the best way to do it anyway. I say without considering energy, although everything's really got energy in it somewhere. But yeah, that average velocity times time is just so much better anyway. Now consider energy. What is the initial kinetic energy of the rail car and the initial kinetic energy of the projectile in both directions? Right, so kinetic energy for the car is a half, how heavy was it? I want to say 200 kilograms. Yep, 200 kilograms, 100 meters per second. So a half times 200 times 100 squared. So that's 100 cubed. So that is 10 to the 6 joules. The horizontal kinetic energy of the projectile. So a half times, mass was 10, wasn't it? Times, well, that was 100 as well. So yeah, we just ended up with something considerably smaller on that. So that's going to be what we got, 10 to the 5, halve it, so 5 times 10 to the 4 joules. And then the vertical kinetic energy is going to be a half times 10 times, oh good grief, yeah, this is, what do we have, 200 sine 60, so 200 times root 3 over 2 squared, so 100 squared times 3. But let's write it all out. So 200 root 3 over 2 all squared. So we cancel that to make 100, 100 squared times 3. So we've got 3 over 2 times 10 to the 5. So let's not start adding in fractions when we've been working without them. 1.5 times 10 to the 5 joules. But that took longer for 3 marks than some of the others. Use your calculation of projectile's initial kinetic energy. Again, calculate the maximum altitude. So what was our vertical one? 1.5 times 10 to the 5. So 1.5 times 10 to the 5 will be equal to mgh. So that's 10 times 10 times h. So we're just knocking 2 off of this 5 here. So h equals 1500 meters, which is what we showed before. When the projectile lands in the rail car, why does the velocity of the car not change? Okay, so this is going to be to do with conservation of momentum, isn't it? So we've got, both of them are constantly moving with this 100 meters per second when they're in the horizontal direction. So when so let's say, so both are traveling, it's going to be a hard one to put into words, I think, at 100 meters per second horizontally. So we're saying, what is this? Why does the velocity of the car not change? Therefore, v horizontal for projectile is unchanged on landing. Let's try and get a sort of chain of reasoning here. Therefore, no force from car on projectile, because that is Newton's second law. There's no change in momentum going on there. Therefore, no force from projectile on car, because that is Newton's third law. So at least we're bringing in some, key ideas on all of this and giving a reasoned argument, a chain of argument. So what is that? Why does the velocity of the car not change? Oh, right, okay. Therefore, so we have to put in another one. No change in car velocity, because that again is Newton's second law. We got no force, we got no acceleration. Right, okay. Assuming that the projectile remains in the car, what is the combined kinetic energy of the car plus projectile after it's landed? To 3 significant figures. Right, so half mv squared, so a half times, so it was 200 kilograms plus 10 kilograms, so that's the total mass. It's still moving at 100, so we just need to do that. So that is 105 times 10 to the 4, which equals 1.05. That must be what I've got the 3 here, times 10 to the 6 joules. All right, so that's pretty good. And right, that's the end of it. Right, so we're done with that. That was a swift question, but you kind of expect that for a projectiles question. My hopes were up as soon as it started off and it mentioned projectile in the first half of the first sentence. You think, yeah, this one isn't going to be too bad, and so it proved. So happy days. That completes PAT 2010.